Welcome in. All right, so learning epsilon-delta proofs, you have to take it, a little bit step by step. What I'm going to do in this video is just to show you how to do epsilon-delta proofs for any linear function. So what does that mean? If you are given a limit and you're asked to do an epsilon-delta proof for it, so by your professors. So if someone gives you an epsilon, you're supposed to find the delta for this given epsilon such that this condition holds true for all of the x. Okay, so how do we go about in doing this? Now, I explained this limit definition and I'll put up a link up above there. So I'm not interested in explaining the actual definition itself. So you can look in that video if you want to. This is exactly what we want to be able to do visually, and I'll show you through some decimals, kind of calculations, okay, and then some little bit of programming that we can find any delta for a given epsilon when these functions, so this function right here is just a linear function. And that's step number one. Learn how to do that and understand it well, and then you can move over to quadratics, okay, which I will also do later on in a different video. You can do cubics, you can do absolute values, whatever parent function you have, and you can combine the parent functions and do any epsilon delta proof. So here it is. So here are the steps that we want to be able to take. So for any epsilon delta proof, you're going to be doing two things. Interestingly enough, step number 2 is very often forgotten, and then students are docked marks by their profs or by their TAs. So in step number 1, this is what everyone is looking for. They want to find a delta for a given epsilon. And now how do you do that? Well, you do it through creating a connection between these two, which of course is coming straight from the definition. So I want to show you how to do that. Once you establish your delta, then you move over to step number 2, and then you have to show that if you are within this bound, then this right here is going to be within an epsilon. All right, let's give this a shot. So step number 1, so this is something I'm going to copy, and I'm going to do it on several examples. So here are the examples that you have. Notice that they are all linear. So this is the function, 2x. So the slope is 2 for this function. The y-intercept is 0. Here is another linear function, 0.5x, so that's the slope, and then the y-intercept is -1. Here's another linear one. So now this one looks a little different, but it's nothing more than -4 is the slope, and then the 2 is the y-intercept. And here is the general linear equation. And I'll show you that for any linear equations, what the delta will be. So we're going to take step number 1. So I'm going to paste this back in here, and we're going to go and walk through this thing one by one. So let's take this example, which is going to be our first example, the simplest one. Let's paste it back in here. All right, and let's try to go through this. So step number 1, we want to find a delta which is greater than 0 for a given epsilon greater than 0. So that's typically something that you will write. So don't just jump in and start making connections. Actually make this statement first. Now we want to make the connection in between these two. So we want to connect these two things. This is, of course, related to the delta, and this is, of course, related to the epsilon. So how are we going to do that? Well, so for the given limit, notice that if I rewrite these, so I'm going to have x minus, the a really is 2 because x is approaching 2. So that's what I have there, right? Now, the other one, which is going to be f of x, which is 2x, your limit is 4. So that's what we have right there. So that's the second thing that we have. Now, we are given an epsilon, which is greater than 0, right there. So our entire goal will be, let's make this and connect it back to here. So how am I going to do that? What I am looking for is, I am looking for either factoring of some kind, or I am looking for some kind of a connection between this right here so that I can see an x minus 2 as a factor of it. So I will very quickly notice that there's a 2 and a 4, so I can factor out a 2. And that factoring out, what it will give me is x minus 2 in the brackets. This is all in absolute values. I'm going to ignore the less than epsilon for the moment. But this is exactly what we want, right? So here is the connection. So now I have an x minus 2 and an x minus 2. So I'm going to relate these two things back together and find my delta. Now that 2 that I have in here, so I can take this outside because that will make no difference. So this is going to be 2. And notice x minus 2, which can be rewritten. This, now I'm going to bring back the less than epsilon right here, is now the connection I want. So just like you would be solving, so if you would be solving for this entire thing, now this is an inequality, so I can take this 2 and now get rid of it by dividing both sides by 2. So if I take this and I divide by 2, it does not change the inequality in any way. So this now cancels out, and what I have is now x minus 2. That epsilon, remember, is given to us, and we're saying, okay, we're going to be dividing it by 2. And this is now basically what you have been looking for, which is the establishment of your delta. So this delta that we see right here, that's what this delta will be. So delta is dependent on epsilon. Yes, it will be dependent on epsilon because epsilon can be changing. It can be made bigger or smaller, and therefore you can then adjust your delta. So now what I will do is I'm going to say, all right, this looks exactly what I wanted. So notice if I go back to the original, this was supposed to be greater than 0, and it was supposed to be less than a delta. And now this right here is what I wanted to have, and I found it right there. So notice that what you have all the way within here, here's your x minus 2 less than, and now this whole thing is going to be set to delta. So this is going to be epsilon over 2. So meaning if anybody gives you an epsilon for this given limit, you can set delta to epsilon divided by 2. And what we want to now see is that our condition holds. So what do we mean by the condition holds? Well, now this is what is often very much forgotten, and sometimes students will lose marks depending on how strict your TAs or professors are. But if you leave this and you say this is your delta, indeed it will be the delta that you need, but you need to now show that this delta actually works. So how do you do that? Now this is kind of redundant. However, what you're looking for is this. So you want to show that if your x is within this bound, right? So if it's within this bound right here, then this condition is holding true. So let's give it a shot. So we're going to assume that we have our x minus a is going to be less than, this is epsilon over 2. Then, so what we want to be able to now see is our f of x, which was 2x minus 4. This is supposed to be less than epsilon. However, you saw from above that this is nothing else but simply 2x minus 2. So we have seen that right here. And now this is where our substitution comes in. So this right here is now less than epsilon over 2. So what I will do is, okay, so as you have that, I'm going to set this, and I'm going to say this is going to be 2. Now substitute, so now we're showing, this is going to be the substitution that I have. The 2 and the 2 cancels, and of course this is equal to epsilon. And we have now shown that if you have your x within this bound of delta, then what you are looking for is this 2x minus 4, which is fx minus L, is less than the epsilon. And now we have shown, okay, the teachers, TAs, professors, that indeed this delta works. And now visually, what does this mean? So if you now take this, okay, I'm going to bring in decimals. So here is your linear epsilon. So what I'm going to do is, notice the function on the left-hand side. I'm setting the slope equal to 2 because that's what it was. And then my b, my intercept, was just 0, right? So that's what I wanted. Now, I didn't draw the entire f of x, okay? So within here, it's only a portion that is drawn out. But I have now set any epsilon that I wanted. And so here, I can now shift this epsilon, okay? Make it really small, make it really large. It doesn't matter. And it adjusts what the delta is. So that delta, okay, that we see there is within the x. So notice it is around 2. So my a was equal to 2. My limit was equal to 4. And now if someone gives me the epsilon, I am always going to be finding the actual delta. And this now is showing me what I needed to do. Now, of course, the delta can be smaller than epsilon over 2. It could be epsilon over 4. It could be anything that's smaller, and it will work. But anything bigger will not work. All right? So here is a visual of how that delta and epsilon in terms of that simulation will work. I'm going to attach this decimals graph to the video. You can link it below and then play around with the decimals, and you can open it up as well. And then you can see how I've actually set these things up in case maybe you're a professor. Okay, so that is one example. Now, doing one example is not enough. Now, if you've understood it, amazing, right? But you have to start doing several of these examples. Now, I'm just concentrating currently just on linear functions. So that's what I would want you to see. So now let's take a look at another example. So here is B. So what if now you do have, so I'm going to take this, what if you do have an intercept, right? So what happens now? Oh, well, that's okay. Let me just take this as it is. And we're going to be working on with this one. So once again, what do you do in this epsilon delta proof? So if someone asks you, okay, to show that this is true, then once again, what we need, so well, we need this statement, okay, right here. So I'm going to borrow this, copy it. I'm going to paste it back in here. So that's our first statement. Now, our second thing that we want to be able to do is now we want to be able to now make that connection in between. So let's write out the following. So we have an x, now notice this is going to be minus, this is -1, that's our a, so that's right here that we have. And this is going to have to now get connected in, so this is going to be x really plus 1, that's what we'll have there. And now we want to connect it back in to f of x. Now in this case, f of x is 0.5x minus 1. That's f of x. I'm going to put it in brackets. Minus, notice, -1.5. That's my limit. Now within this, this is supposed to be less than the epsilon, okay, which has been given to us. Okay, so let's now massage it. Okay, so a little bit, and let's see exactly what happens in here. So I'm going to simplify this. So the first thing that I'll do is, okay, so I'll open up, okay, the brackets, Notice this is going to be -1. This is going to be plus 1.5. And now, so of course, these two, I can just simplify this further. So this is going to be plus 0.5. And this, of course, again, still has to be less than epsilon, right? So as you're going through, you can certainly write these in. And now the same thing. So notice what happens, okay? So this and this, it has the same factor, 0.5. So I'm going to take out the 0.5 out of here. And what I'm going to have remaining is x plus 1. And once again, notice now I have established a connection between this and this right there. And what do? Just as in the previous example, you're going to now take this and you're going to be solving for that x plus 1. So you're going to be dividing both sides right there. So that's going to get rid of this. It does not change the inequality again. So this is what we have right there. And we have x plus 1 less than, and now epsilon divided by 0.5. So now what we will say is, all right, let's set. So now set our delta equal to epsilon divided by 0.5, okay? Or in other words, this would have been just simply 2 epsilon. So that's what you would have had for your delta. Now, step number 2, so this is the next component. So that's this right here, right? So we have to now show that the delta actually works. All right, so let's do that. So I'm going to take this, borrow it out of here. So let's copy it. And this is if you were showing the full proof to your profs. So this is what you would have. So now you set, all right, so we want to have this, which is going to be our x, now minus a, which was really plus 1, right? Because it's negative and a negative. And now we've set our delta. So if you write epsilon over 0.5 or 2 epsilon, so we'll make the epsilon twice as big, okay, for the delta. And now we want to be able to show, so as we're going through, that what we have is that f of x, well, in this case, so I've already written it out, so let me copy it in here. We want to show that this, let's duplicate it, bring it back, and I'll get rid of that blue bracket there. So we have this, and of course, so this was just simply equal to now, so from here, 0.5, and this was x plus 1. Okay, so that's, I'm just simplifying this. Okay, so this just comes out, the 0.5 comes out. Could have taken it out right away, x plus 1. And now notice that this is going to be less than, because this right here, okay, notice this right here is less than 2 epsilon. So if you substitute that in, you're going to get 0.5. Okay, and this is 2 epsilon. So 0.5 and the 2 is gone, and that means that it is less than epsilon. And you've now established that that delta works for any given epsilon. So within here, so as you're going through, so again, so what you have, you are saying that f of x minus L is less than epsilon, right? That's what you wanted to establish. Now, of course, you can still finish. You can write in here. So therefore, for any given epsilon, the delta is equal to 2 epsilon, or epsilon divided by 0.5. And you've now shown an epsilon delta proof for this. And again, so if you were doing this right here, so if I now change this back, so let's take up decimals, and here's the visual. All right, so here it is. Okay, so you have it. Okay, so notice it's centered around -1, right? The limit was -1.5, and now we have the delta, which is necessary, right? So as you're going, and you can certainly make this much larger, you can make it much smaller, whatever it is that you need. And you can just start adjusting this. So this is visually what is happening. So someone gives you an epsilon, now you're finding that delta, within the bounds. All right. Okay, let's do the next question. All right. And now again, you know, you can begin. So make sure that you're stating that you're finding. So what you want to do is you want to be able to find this, right? So make that statement. So copy it just so that you get used to it, so it makes it much more formal. So you want to find a delta greater than 0 for a given epsilon, which is greater than 0. Okay, so now within here, so let's do a walkthrough. So what do we have? So we want to do again an establishment. So making a connection in between. So in this case, it's going to be x minus a quarter. All right. So that's what we have in there. And the connection has to be made with f of x. Now notice in this case, it's 2 minus 4x. All right. That's your f of x right there. I'll put it in brackets. And then minus 1. That is your limit that we're looking for. This is supposed to be less than epsilon that we're trying to make the connection with. So once again, so now as you're going through, just simplify this. So if it's linear, just go ahead and simplify it. So things will kind of start falling apart for you. All right, so as you have this, so this is going to be 2 right there. And this is minus 1. So it's going to be 1. That's going to be 1 minus 4x. All right, so here it is, less than epsilon. Now, you might say, well, I don't see any connections here, right? 1 minus 4x. Well, so you have to be a little bit clever, okay, in terms of trying to see this, because of the fact that this is a fraction, right? You wouldn't normally, especially if you came out from high school and you're not familiar with this, you wouldn't think that this has any factors, right? So it doesn't have any factors per se that are whole numbers. But notice that you can indeed do the following. So you can say, let me, so that I'm cheating here. So here, what I am looking for is, I really want this x minus, okay, 1 over 4. So I'm going to readjust this. I'm going to say this negative 4x plus 1. All right, so I'm just rewriting this. And now, so take a look what I'm going to do. Because I want x here on its own, I am going to, so right here, so I'm going to now take out the negative 4. Now taking out negative 4. So I'm going to do this. And now notice this is going to be x. And now this is going to become minus 1 over 4, right? Because if you now factored out negative 4, if you brought it back in, you would get this. And if you put this back in here, this again would become a plus. And the 4 and the 4 would cancel, so you would get your 1. So now you have to do that, because what we want to be able to establish is some connection. Notice, these two, I would want them to be the same. So within here, so as we're going through, now this negative, you might think that it's causing a headache. It is not causing a headache for us at all. So in fact, so notice that because we have absolute values, all right, so I can do this, x minus 1 over 4. Okay, so, and you can write 4 in here right away. And then you would have x, this right there, and then again, so don't forget, okay, your epsilon within here. So once again, so take your 4, divide both sides right there. So this is what we're going to have. And now, so this will cancel out. So this will cancel out. So as you're going through in here, so it's going to have x minus 1 over 4 less than, and this is your epsilon over 4. And now you can say, yeah, I'm going to set, so this is, we're going to set our delta equal to epsilon over 4. That's what we will have in here. Now you can go back and check, right? Does this work? So just the same thing as we had done in all of these. So again, I'm going to steal this out, duplicate it, let's put it back into here. right? So let's put it like this way. And so for this right here, so for us, this is x minus 1 over 4. And our delta we've set to epsilon over 4. And does this imply that this is true? So, in here, now we've done this already. So again, I can copy this down right here. Let's copy it. Let's put it back in here. And let's clean this up a little bit. Now, we know so that all of this was just simply equal to, so notice because we stepped through this, okay, so as we were going through here. So now you're just basically repeating all of this. So it would have been, so this is simply 1 minus 4x, all right, so that's just simply equal to that. And it is equal to, so notice, negative 4 and x minus 1 over 4. Okay, so I'm just factoring out the negative, right? So within here, and now this right there, okay, you can now substitute, it is less than, so now you do have to show, so this is now, okay, less than, it's going to be negative 4. And this is epsilon over 4, so it's less than that. And then this and this cancels, and then you have now shown that f of x minus L indeed is within the bounds of epsilon, right? So this is what you would have. And now again, you can now show, okay, so that this is the desired delta. And if we switch this back in, let's take a look here. What I want to show you is that for this example, what we had was negative 4 was your slope, and then 2 was your y-intercept. And there you have it. All right, so here it is. Okay, so we have to adjust the slope, the intercept, and also actually the x is approaching, so the a itself had to be shifted over. All right, so that's what we have for this, okay, example. The last example is the general case. So I'm not sure if you've noticed, okay, there's a pattern here for all the linear ones. The pattern is that the delta itself is actually equal to always the epsilon divided by the absolute value of the slope. Okay, so by the slope itself. That's what it will be for all linear functions if you're doing limits. So, for instance, that I gave this example right here, which is just a general one. Now, this isn't anything magical. It shouldn't surprise us. A linear function itself is defined everywhere, right? All the limits exist, you know, so we don't necessarily need this epsilon delta for proving. However, when you're learning this, it is good practice to do the epsilon deltas on simpler limits, just like this one, so that you can understand the pattern, like what is it that I'm going to try to do when the functions get harder. So here for the last one, I just want to show you what happens. Now, I'm not going to go through the entire thing. So as we're going to be doing this, you know, I won't make it as formal, but I just want to show you what happens and how you can now find your delta. So let's imagine, you know, we made our statements and so on, but notice what happens here. So if I now take, so this is my f of x, right? So what we're going to have is mx plus b. Now, we are going to assume that m is not equal to 0, because then we wouldn't have a linear. It would just be a constant, okay, b, right? A flat line, a flat line for the y. Okay, so here we're going to assume that the slope is not 0. It is actually something. Now, minus, and this is ma plus b. All right, and this is supposed to be less than epsilon. Now, what we want the connection with x minus a, right? So that's what the connection we are looking for with the delta. So when you simplify all of this, what you're going to get, so notice you're going to get mx minus ma. All right, I'm going to group these things together so they both have m in it. And now notice that the b minus the b is gone. So once this is gone, then this whole thing just simplifies to this. But hold on a moment. This is just equal to, so notice I can factor out the m, and I'm going to get x minus a. And that's exactly what I wanted, right? I wanted this relationship. And, you know, so this is supposed to be less than epsilon. So now what I will do is I'll divide both sides, notice, by, now you do have to put it in absolute values, the slope, because the slope is not always positive. It could be negative, right? So just keep it in absolute values so that this cancels out. And then here is your delta. So your delta is equal to epsilon over this. And that will be true for all linear functions. So that's what you have. And that's exactly what I have been doing within here. So when I am graphing it out, notice that if I scroll back down here, so notice now here at the top, delta is equal to, that's what I was doing right from the start. So epsilon over that, because that's what it was. Now, if you know this, and now if you get anything from homework, assignments, quizzes, tests, wherever it is, okay, so typically in calculus or in some kind of math in university that you're going to be doing these epsilon delta proofs, you now are hopefully well prepared to see it. Walk through these examples, see what I was doing, and then now I've generalized it for you for all linear functions. That is it. That's what you do. Now, of course, once you find your delta, now you have to do that annoying step of confirming that that delta will work. So you have to go and do that final step. So don't forget that, because I used to forget that and I would lose marks. All right. Thanks for watching. See you in future epsilon delta proofs. Bye, everybody.